years ago, and we are delighted to welcome her back. Vera works mostly in the philosophy of physics, with a connection to metaphysics. She has published on these topics in leading journals such as Foundations of Physics, Synthèse. She has broader interests. She also has done work on the methodology of science. She has published on the concept of replication in recent years, including papers in Inquiry and other journals. I will mention two books by Vera before finishing this introduction. She is the author of The Metaphysics of Bohmian Mechanics, published in 2022. And she's the editor of a book that grew in part out of an event in Pittsburgh, Philosophy of Astrophysics, published in 2023 with some other Pitt-affiliated philosophers. And like many of us, she also has put a toe in the philosophy of AI and in AI in her ongoing research. So Vera, it's really wonderful to have you back. Floor is yours. I will mute myself and turn the camera on, but if there's anything, I will re-emerge. All right.
Thank you so much, Edward. Thank you for having me today, and thank you all for being here. So it's really a pleasure for me to discuss my research with you. And so let's get started. So I'm really sure that everyone has heard about this news, like, oh, we discovered water on an exoplanet, or we discovered hydrogen in the atmosphere of another exoplanet. And, why we read this news, so maybe some questions pop up in our mind, which is, well, but are these claims really reliable? How do they reach these conclusions? And if we are philosophers of science, as we do, then one of the questions is really how to evaluate the epistemic significance of those claims. Is it really the case that they discovered water on an exoplanet? So then here is the problem. So exoplanetary science, as many other empirical sciences, is based on sparse, uncertain data. So then what we really need is to build up a complex modeling procedure, complex modeling techniques to provide a representation of the system. In this case, for instance, the atmosphere of an exoplanet. And we, of course, know that if these modeling techniques are complex, then they will also require modeling choices, modeling assumptions that sometimes are a little bit tricky. So then, of course, the question comes up. But is really the representation provided by this complex modeling technique cogent? Is really reliable? Can we really take it as epistemic evidence for our scientific knowledge? So the plan for today is that, I would like with you to investigate epistemic status of atmospheric retrieval models that are complex modeling techniques used in exoplanetary science to model the composition of the atmosphere of exoplanets. And in my talk, I will utilize a nuanced approach. That means that, of course, my aim will not will not be to establish that yes, that retrieval models have an epistemic status or they do not have an epistemic status. My approach will be nuanced in the sense that I will consider them as heuristic tools that, however, do have an epistemic saliency, and we'll discuss this later. So basically, my talk will not be based on a dichotomy between what is an heuristical tool and what is an epistemic tool in the methodology of science. So in order to investigate the epistemic saliency of these models, I will check, first of all, the structure of this model and the relation with data and the theory. Then I will check the function of this model, which of course is a representational function. And then I will also discuss to what extent these models suffer from the problem of inconsistent or incompatible models. And finally, I will utilize the meta-empirical confirmation framework developed by Richard David as a means of discerning and appreciating the epistemic significance of these models, the atmospheric retrieval models. So I do think that this framework provides the right tools to discern and appreciate to what extent these heuristic tools can be epistemically significant. So just let me tell you a little bit about this work and how it was initiated, how it was born, because it might be also interesting for you. So it all started at the Center for Space and Habitability when I did, where I did my postdoc, and in particular, the focus of the center is exoplanetary science, and they are particularly strong in atmospheric science. So what they do is to model the atmosphere of exoplanets. And this center was born to foster dialogue between the sciences interested in atmospheres and exoplanets and the humanities. So it's really a great place to visit if you're interested in exoplanetary science. So, to start, I would like just to give you a framework of exoplanetary science and why we need these atmospheric retrieval models, okay? So we know that in the past 3 decades, more than 5,000 exoplanets were detected in the universe. And we know that exoplanets are planets that do not orbit around the sun, but they orbit around other stars that are not the sun. So they belong to other solar systems. And unfortunately, we know very little. We know very little about how they were formed, how they got the shape that they have. We know very little about the inner composition, but also about their atmospheric compositions. So there is a really great of ignorance, a great amount of ignorance surrounding them, okay? And this ignorance is due to different difficulties that here I group in different types for different reasons. So the first reason is that, of course, the Earth cannot be a good analog to inform knowledge about them and also about their atmosphere. Why is this? So, well, because they manifest the features that are and can be drastically extreme and drastically different from the features of the Earth. For instance, there are exoplanets like the Inferno, like WASP 76b, whose atmosphere features vaporizing iron and calcium. So it's really like hell. And of course, Earth does not feature anything like this, okay? So basically, we have no or very little background knowledge about their conditions. We cannot really guess what their conditions could be, okay? They could be really extreme. A second reason, which is obvious, but it's worth mentioning, is that, of course, until now, it's not possible to perform in situ measurements, okay? We cannot land on exoplanets and we can't really send the probes to capture molecules of the atmosphere of exoplanets. Of course, we can send telescopes to kind of observe things that happen around the exoplanets, and we will see this in a minute, okay? And of course, we can get data that are really promising, okay? But this sometimes is really not enough to break the ignorance, the deep ignorance that we have about them, okay? Also, the other important reason for our ignorance is that even direct observations are almost impossible. Even if the telescopes go there, it's very rare, if not impossible, to directly observe them. And this is because their light, so the light of the exoplanets, get extinct within the glare of the parent stars. That is so much that, of course, it hides the light of the exoplanet. So that's what would be needed. Of course, so the idea would be that we need to suppress the glare of the parent star with some coronagraphic instruments, for instance, an occultator. But this is usually not enough, because even if we manage to put an occultator in front of our telescopes, that it's not enough, as the data that we get is just too noisy to be reliable. So usually astrophysicists prefer using other techniques, and these techniques rely on indirect detections, okay, and observations. So these are indirect strategies to get some knowledge about the atmospheric conditions of the exoplanets, okay? So the most important one is the transit technique. So what does this transit technique amount to? So basically it amounts in just waiting. So we wait that the exoplanet passes, and it's aligned perfectly between us and its star. Okay, so it has to pass between us and its star. And of course, if we see a blockage of light, and if we see something black, a black spot, that it means that that is an exoplanet, that there is an exoplanet. And the amount of the light that is blocked is, of course, proportional of the size of to the size of the exoplanet. Okay. So, of course, when we observe a black spot, we say, oh, we discovered an exoplanet. We see that there is an exoplanet. But not only that, indeed, we can also detect if the exoplanet has an atmosphere. So if we see something that surrounds the planet and it's a little bit fuzzy, such that it's really impossible to really distinguish clearly the border of the planet, that it's very likely, it's very promising that the planet has an atmosphere, okay? And from this, we can actually study the atmosphere, and I'm gonna explain how, okay? So of course, the light of the parent of the star of the exoplanet filters through the atmosphere, and so through the molecules that, of course, that make up the atmosphere. Okay, so then the stellar light filters through the atmosphere, and of course interacts with the molecules by scattering, by absorption. Okay, so then it is possible to obtain a spectrum, an absorption or transmission spectrum, by measuring the depth of a transit light curve at different wavelengths. Okay, so we get the spectrum, and then, of course, if there is no atmosphere, the spectrum would just show a flat line. But if there is atmosphere, then this spectrum would show a pattern of absorption and transmissions. Okay, and then our job would be to read and interpret the spectrum. Okay, how is it so? Well, we know the different chemical elements of an atmosphere absorb and transmit lights with different specific patterns of wavelength. Okay, so then when we get the spectrum and we see valleys or peak, okay, well, those are the signature of the chemical elements that, or the molecules that are responsible for those signature, okay, for those patterns in the spectrum, okay. So then the job is to interpret the spectrum, okay, and to infer the kinds of molecules that are responsible for the patterns in the spectrum. And of course, here spectroscopy plays a crucial role. Why is it so? Well, because we usually have only the spectrum, the spectra as our evidence, as our empirical data. And, because from the spectrum, we can derive many useful pieces of information, such as the chemical composition of the atmosphere. But then from the chemical composition of the atmosphere and the abundance of the different chemical elements, we can also directly infer, for instance, the mass of the planet and the habitability of the planet, or the formation of the planet, the history of the formation of the planet, okay? So then the question is whether spectroscopy is a sound discipline. If it is not a sound discipline, then I would say that the whole exoplanet science would really be in big trouble, okay? So spectroscopy is a sound discipline. The problem, however, that it faces is the problem of interpretation, the problem that we have to interpret the spectrum. This is not really an easy job, and now I'll tell you why. So what is the problem of interpretation? Well, interpreting the spectrum, right, means inferring what are the chemical elements that are responsible for the different patterns. So it means being able to identify the signatures of each element. And this, of course, is a task that faces various challenges. First of all, because we have a very noisy spectrum sometimes, okay? So our data is uncertain, okay? Also, once we have the spectrum, we need to disentangle all the information. We need to say, okay, well, this peak is the signature for this chemical element, and this valley is, however, the sign that there is another chemical element, okay? So we really need to disentangle the information provided by the spectrum, okay? Also, on the top of this, it could be that there are some haze or clouds in the planet that makes everything much more difficult and confusing, okay? Because then the spectrum would not have, the kind of profile that we would suppose it to have without, if the planet had not haze and clouds, okay? So haze and clouds interfere with how the light is absorbed and transmitted by the difficult chemical components, okay? So then basically astrophysics have to face the problem of degeneracy most of the time. What is this problem of degeneracy? This is basically an underdetermination problem. It happens when the same spectrum can be matched with different models of the atmosphere. Okay, so we have a spectrum and we could infer many different compositions of the atmosphere. Okay, they are all equally compatible with the spectrum. Okay, so typical case of underdetermination problem. So this is where, and this is why, atmospheric retrieval models are extremely important. They are really indispensable tools to overcome the problem of guessing the atmospheric composition of the exoplanets, okay? So these models are based on the inverse modeling method. So from the data, we kind of infer inversely, okay, the chemical components that were responsible for these features in the spectrum, okay? And they are indispensable because in this way, we can overcome the problem of the lack of direct measurements and the lack of direct observations, okay? So let me tell you a little bit how these models are built. Okay, so first of all, they have two different parts. So even though they are called the retrieval models, and so it might seem from the name that they are just the inverse modeling procedure, actually they consist of two different parts, two different components. We have a forward model and we have an inverse model, okay? So with the forward model, we can, if we hypothetically put or decide an initial state of the atmosphere, okay, with some temperature profile, chemical components, pressure profile, we can, through the radiative transfer model, which is derivable from conservation principles of energy, we can infer and we can predict what is the spectrum of that atmosphere composition would have, okay? So basically we decide we guess what the initial state of the atmospheric composition could be, and then through the forward model and its radiative transfer part, we can predict what the spectrum would be. This is, of course, an artificial fake spectrum, okay, that we didn't actually got empirically. So it's called the synthetic spectrum. And this is a very unrealistic spectrum because it does not have uncertainty, okay? So it's very polished. So what we do is with an instrument model, which is built inside the forward model, we can downgrade this synthetic spectrum to a spectrum that really would really much resemble a real empirical spectrum that is the one we get, okay, or with, in real life, okay? And then we can input this downgraded and more realistic synthetic spectrum in the inverse model, which is the second component, okay? And then here, this inverse model can compare the real spectrum, and so the observed data, okay, that we input, okay, with the synthetic spectrum, and decide by Bayesian statistics if actually they two match, okay, with some sort of course probabilities. So then if the comparison is promising, okay, then, and actually it's very convincing, then the inverse model stops here, okay, and informs us that it found the right composition, the true composition of the atmosphere, or maybe the most probable composition of the atmosphere. But if the comparison doesn't lead to a very good optimistic result, then the inverse model goes back and tries in the space of possibilities, so in our parameter space, to guess what would be the kind of atmospheric composition that could be more probable, okay? And then reiterates the check, okay? So this is an iterative kind of process that continues until the model finds the best fitting composition of the atmosphere, the best fitting retrieved quantities that would match the real spectrum that we have, okay? So this is how this model works, okay? So then the question here is whether this retrieval models do have a certain epistemic status, okay? So we can say that the whole exoplanetary atmospheric science inherits its justification and its epistemic authority from the epistemic status of these models, because they heavily rely on these models, the retrieval models. So then the question is, are atmospheric retrieval models epistemic sources of knowledge? Are they reliable? Do they provide a cogent, reliable representation of the target system, and so the atmosphere of exoplanets? Okay. So here we can actually say a little bit more about this dichotomy that sometimes is present in the literature, and that distinguishes between heuristic tools used in science and scientific method and epistemic ones that are truth conducive, okay? So usually we could call heuristics the set of strategic shortcuts, inference rules, or mechanism that avoids scientific teams to come to conclusion kind of quickly, even though it does not have all the relevant information, all the information that is relevant to make a real optimal decision, okay? So then, of course, we know that heuristic strategies do not, we should not expect that they actually produce or provide truth-conducive solutions. Not correct, nor not optimal, okay? We know that they're just pragmatically justified, okay? We have limited resources of time, limited resources, maybe also financial resources. And so, we cannot really spend too much time on this, and then we use the shortcuts inference rule, okay? These heuristic tools are not properly epistemic, and so they cannot count as genuine pieces of epistemic evidence. In this case, we would say, well, if atmospheric retrieval models were just heuristic tools, so they would not be able to provide evidence for the exoplanet atmosphere, okay? On the other hand, we could distinguish heuristics method from epistemic method and say that no, epistemic methods really are truth conducive, okay? Because they take into consideration all the relevant facts, and so they are reliable, okay? So in this way, epistemic methods would produce epistemic evidence in virtue of being epistemically justified. So this kind of distinction between heuristic tools and epistemic methods is discussed in the context of eliminative reasoning in a paper by McCoy published in 2021, okay? My approach, however, is different, okay? So in this paper, I admit, and I fully, or in this talk, I admit and fully acknowledge that atmospheric retrieval models are heuristics, okay? And this is because if I look at all the definitions provided in the literature about what is a heuristic, for instance, the one by Lennart or the one by Winsett, then there is a clear sense in which atmospheric retrieval models are heuristics. They make no guarantee that they will produce the correct solution to the problem, okay? We will see they are very cost effective in terms of resources, okay? And also they perform very well in simplistic idealized scenarios, we will see this, but they are kind of flawed in case of when we have very complicated parameter space and very complex characterization of the atmosphere. We will see this later. However, my point is that, well, if they are used in science, okay, in the way they are used, then they are in any case epistemically good enough. And we will see also that they are epistemically good enough. They can be used and they are to some extent reliable. They are epistemically good enough, okay? And so my talk aims to understand to what extent they are epistemically good enough, to what extent they are epistemically reliable, to what extent they are epistemically salient, okay? And of course, this involves an evaluation of their epistemic limits and their epistemic strengths. And so I will do this, first of all, by focusing on the structure of retrieval models, okay? So one traditional approach for the study of models regards their relations with the theories and data. How do models are related to theory and how they are related with data? So paradigmatically, okay, we could distinguish two extreme types of models, okay? So on one hand, we have theory-based, theory-driven, or forward models that are based on top-down approach, like the forward model that I just talked about before. So we have conservation, energy principle, and from that we derive the radiative transfer model, and from that we derive a possible, the most probable synthetic spectrum, okay? Then on the other hand, we have the data-driven models, also called data-based models or even data models, okay? They, of course, are grounded on the data, okay? And they're based on a bottom-up approach, okay? In this case, it would be exactly from the atmospheric spectrum, we could infer some kind of properties of the atmosphere, okay? So usually forward models have very are strong and are reliable as long as the theory on which they start with is reliable. So they inherit their epistemic justification and authority from the theory they're based on, okay? So the weakness is that, of course, they lack empirical grounds, okay? They're not constrained empirical by data. The data-driven models, on the other hand, and by contrast, of course, they can be regarded as strong because, of course, they rely on what is mostly close to the datum, and so the truth of reality. They have a representational content that we could say, even though very idealistically, that it's immediate. Okay, the weakness, of course, is that sometimes we get very noisy data, and also because they need to be interpreted and manipulated and systematized. We can't use raw data, okay? So then what about retrieval models? Well, I kind of answered already, okay? Retrieval models, of course, are not either forward models, theory-based models, nor, of course, data models, because they include both of them, okay? And so they should be regarded as hybrid models, okay? And so this, I think, constitutes a very new, interesting case study for philosophers of science, okay? They kind of break this dichotomy sketched between database models and the theory-based models. So one could say, well, look, there is a whole tradition in philosophy of science also to regard models as mediators between theories and data, okay? These are models that, are not derivable neither from the theory nor from the data, and they are mediating between them. So maybe they fit with this. Well, let's remember that these models also are characterized usually by independence and autonomy. So Cartwright and Morrison, they claim that models are characterized by autonomy and independence, and they are built thanks to the creativity of the modeler, okay? So do retrieval models fit with these characterizations? Well, I mean, of course, retrieval models are not entirely derivable from the theories. They're not entirely derivable from the data. They are not reducible to either theory or data, but they don't really enjoy a sort of independence, except for the instrument model built in, okay? So they heavily rely on theories and data, okay? So they are heavily dependent on them. And so the reliability relies on both theoretical principles like conservation principle, conservation of energy, and the data, okay? And so the spectrum, okay? So what about their epistemic value, okay? So one could have a very pessimistic view about them. I could say, well, I mean, they are more vulnerable because, of course, they are rely on both of the theory and the data. If something goes wrong with the theory and something goes wrong with the data, then really they are completely misleading, okay? But let's just look at the mechanism and the structure. Well, my point is that since they are jointly constrained by the theory on one hand and the data, then of course their epistemic justification is inherited through both top-down and bottom-up approaches. And to my mind, this makes them more reliable than a pure database or theory-based model. Okay, so they have a structure that makes them more reliable. Okay, so then it seems to me that the final result should be more cogent, okay, than just compared to just models that are theory-based and models that are just data-based, okay? So now let's look at the function of atmospheric retrieval models, okay? So of course, most of the astrophysicists I talk to, they are realists and they want their models, the atmospheric retrieval models, to represent the target system. They want to have these models, they want to have them a representational function in terms of mapping to states of affairs and also an explanatory one. They want these models to explain why they get a spectrum instead of the other one. They want their atmospheric composition of the model to explain why the planet has a certain rotation instead of another one, okay? So atmospheric retrieval models are supposed to have a representational function and to play the role of providing epistemic evidence for true claims about the composition of the exoplanet atmosphere. That's the goal. That's the expectancy, okay? However, here comes a very challenging problem. And so the fact that retrieval models are vulnerable to the problem of inconsistent models, okay? So this problem has been discussed in the literature of models by Frick, by Morrison, and many, many others. And these problems arises when we have incompatible or inconsistent representations of the very same target system, okay? In this case, the atmospheric composition, okay? And this is clear when we study different models and we compare them through an intermodal comparison. So this is the study of Barstow et al. In 2020 that focuses on 3 different retrieval models, Taurex, Nemesis, and Chimera, so based on 3 different algorithms. And the intermodal comparison is usually based on 3 different steps, so we will see them more clearly. So the first step is to try to compare very idealized forward model. So just the forward part of the model. So here it was already difficult to get identical results. So basically these models had just one gas, so one kind of chemical composition, uniform, okay, homogeneous, okay, and still it was kind of difficult to get identical results because, of course, in this complex modeling procedure, there are many different assumptions that should be made. Okay, for instance, about gravitational acceleration, how this might have an impact on the way the light and the gas interacts. Okay, so but if we set everything identical, so all the different assumptions, so that we get results that are compatible. Okay. Then we get to another stage, which is to compare more realistic forward models. And here already we see that most of the models differ at the level of few tenths of a ppm. So basically, if our error margin is very low, then we already see, some differences. Okay. And sometimes, there are also differences at the level of several tenths of ppm, like 60 or 80 or even 100, okay? But things get very serious when we compare the final results of the retrieval models, okay? So in this case, what we do is that we use one model, we get its synthetic spectrum and its associated retrieved quantities, so the quantities that the model has retrieved as the ones that characterize the atmosphere composition, and then we input those spectrum and those quantities into the other two models as inputs, and we ask them to try to retrieve the quantities of the atmospheric composition. And here we see that there are very substantial differences that makes the models incompatible. So the difference at the level of several tenths of ppm, like 100. So very great differences that makes the models incompatible. Okay, so what can we get from this? Well, one possible solution might be to regard these models as perspectival models. This is one solution that was put forward by Michela Massimi in 2019. Okay, well, in order to solve the problem compatible models, we could say that there are different perspectival models, each talking from a particular perspective, each representing the target system from a particular perspective. Okay, so we should not think of the representational function in terms of mapping, no, but in terms of conveying model knowledge. So they tell us what might or might not be possible and what is more probable. Okay, so what they do is that atmospheric retrieval models, they map through the forward models the space of what is objectively possible, okay? And then they decide what is most probable, what is the atmospheric composition that is most probable. And this is done by sampling, testing, gradually eliminating different possible atmospheric composition models. And this is what is done by each of them, okay, from a particular perspective, okay? And in a sense, they provide epistemic guidance. Okay, each of them tells us from its perspective what is the most probable atmospheric characterization. Okay, of course, there are serious limits in this guidance. Okay, why is it? Well, atmospheric retrieval models are based on a kind of eliminative reasoning, and so they inherit all the kinds of problems that we get with eliminative reasoning. For instance, these models might not be looking in the right space of possibility, and so in the space that contains the true solution, the true characterization of the atmosphere. Okay, so we can have a nice discussion, can find a nice discussion of this in McCoy paper on eliminative reasoning. Okay, so this is called the problem of justification of space of possibilities. Okay. Another problem might be that, yes, our models, our atmospheric retrieval models, are looking into the right space where there is the true composition. But actually, they may not identify the best match because, of course, maybe it's too far away. and this has just a very limited a number of iterations. Okay, of course, these models do not explore the whole space, the whole parameter space. Okay, that would be too time consuming. Okay. So what is the epistemic import of retrieval models? Okay, well, we could just have a very weak understanding of it. We can say, as we said before, that they map through the forward models of space, what is objectively possible, decide what is objectively most probable, but given a sort of parameter space and given a sort of code, okay? So then, of course, they are very epistemically salient in the sense that they make some theoretical hypotheses, and they make hypotheses in particular about the profile of the atmosphere. They make it testable. They downgrade the synthetic spectrum by instrumental models, okay? And then, of course, with the retrieval models, we could compare them with the real models and decide what is most probable, okay? Retrieval models can tell us which are the regions of space we should be looking and which regions of space we should not be looking, okay? And all this is about delivering a kind of model knowledge about the target system. And so what might be possible, what might not be possible. And in this sense, they provide a genuine guidance. Okay, and in this sense, we can say that they help a scientific progress, okay, by identifying the best profile, by ruling out rival possibilities. But we are also aware of the problems of these models. We are in particular aware of the problem of incompatible models. And so we should always take into consideration the family that really groups together all the different outputs of all different models. We cannot rely on just one model and its output. We have to take into consideration a family of models with their outputs, okay? So the first conclusion could be this one. Well, atmospheric retrieval models have a much better justification than just the theory-based models or data-based models, of course, because they are constrained by both theory and data, and they do have some kind of representational function that is a model in nature, okay, that is model dimension. But apart from this model knowledge that in any case is very conditional to the kind of code we are using, then retrieval models cannot be considered as pieces of epistemic evidence, okay? So here in the last 15 minutes, I would like to make a proposal. So it seems to me that all this is a little bit too negative for exoplanetary science. And it seems that our evaluation of the epistemic saliency of retrieval models is a little bit too weak. Okay, it would be really bad for exoplanetary science. And my proposal would be to use the meta-empirical confirmation framework and its tool to actually discern and evaluate if the outputs of the retrieval models can actually be reliable or not, okay? So the trick here of the empirical confirmation framework is that we enlarge evidence to include not empirical evidence. This is a strategy that was already employed by Board in 2007 for his account of inference to the only explanation and to make some hypotheses more cogent, okay? So let me tell you a little bit about meta-empirical confirmation. Okay, so this is a confirmation framework that uses some meta-empirical evidence. Okay, and it was introduced by Richard David in his book, String of Theory and the Scientific Method, but then had a greater popularity. It was discussed in other several papers, also by De Bedermaker, myself, McCoy, and others as well. So usually this framework is used in particular cases where we do not have empirical evidence. In this case, we do have empirical evidence, okay? But it will help us, as we will see, it will help us evaluate the empirical saliency of this hypothesis that are based on epistemic evidence, but are not that cogent because of the complex technique of the modeling procedure. So what is the mechanism here? So first of all, one has F, which are some arguments based on meta-empirical evidence, okay? So it could be any kind of knowledge, but the most important thing is that these F arguments based on this kind of evidence, knowledge that we have, should help us increase the probability of a meta-hypothesis Y. And this meta-hypothesis Y is about the limitation to local underdetermination that we will see in a minute. Then in turn, Y, once we increase the probability of Y, then Y will also increase the probability of H, which is our hypothesis, which in the case of atmospheric retrieval model might be the hypothesis of a particular atmospheric condition, okay, or composition. So what is this Y? Well, Y is a hypothesis that tells us that there are no or only a few alternative atmospheric combinations that can be empirically distinguished in a particular specific horizon, okay? And in this case, the empirical horizon is given by the spectrum, okay? So there are very limited alternative atmospheric combinations, okay, that could be empirically distinguished and could explain our spectrum, okay? So then usually the meta-empirical framework uses different, particular 3 meta-empirical arguments that can increase the probability of Y. So here I use the standard ones, okay? And then I will apply them to our case, okay? So in the following, I will really read these different arguments, okay? And we can check how they can be used to evaluate the saliency of our atmospheric condition that is the output of a hypothetical atmospheric retrieval model, okay? So let's start with the meta-induction argument, okay? So according to the meta-induction argument, atmospheric composition that satisfy the same given set of conditions that a particular atmosphere composition A satisfied have shown a tendency of being viable in the past for exoplanets similar to E. So we are considering E, okay, our exoplanet E, and then we found A, a particular atmospheric composition, okay? Well, we know that also in the past, okay, the spectrum that we got from similar exoplanets, similar to E, okay, then they were matched with the same atmospheric composition that satisfied the very same conditions of the atmospheric composition that our atmospheric retrieval model is providing. Okay, so then the fact that atmospheric composition that satisfy a given set of conditions have high chances of predictive success for exoplanets similar to E can be explained by the hypothesis why that there tend to be few alternatives in the given research field under the given conditions. So the fact that also in the past, the same atmospheric composition were matched to spectrum of very similar exoplanets to the one we are studying, then makes us infer that there are very few, okay, few alternatives, okay, about, atmospheric composition that could satisfy the spectrum, okay? So for this reason, the observation is taken to increase the probability that our atmospheric composition is viable also for E, okay? And so that it's trustworthy, that we can trust it reasonably, okay? Then we have the unexpected explanatory argument, okay, that says the following: an atmospheric composition A was considered the best explanation for a real spectrum S. After the atmospheric retrieval model outputted A, astrophysicists found out that A also provides explanation with respect to a range of problems, whose solution was not the initial aim of developing the atmospheric composition. What does it mean? So our retrieval models outputted A as the best atmospheric composition, okay? And then this then can be regarded as the best explanation for the spectrum, right? But then it happens that astrophysicists find out that also for other sorts of problems, okay, for instance, the rotation or formation of the exoplanets, that atmospheric composition A was really the best explanation, okay? So then this effect reveals unexpected explanatory interconnections that can be explained by the hypothesis Y that there are fewer alternative hypotheses in the given context. Okay, then there are conceptual aspects of phenomenology that await explanation. So it means that, you know, this unexpected explanatory interconnections can be explained by hypothesis that there are no many alternatives. Okay, and this is an indication of the viability of our hypothesis H. And for this reason, this observation is taken to increase the probability that our output, our atmospheric composition, that is the output of our retrieval model, is viable for our exoplanets. And then finally, we have the non-alternative argument, okay? This is the standard one. Scientists have looked intensively for a considerable time for alternatives, but they haven't found any, okay? They are better than the best match, okay? This can be explained by the hypothesis Y that there are few or no possible alternatives to our hypothesis H. And this is taken as an indication of the viability of hypothesis H, okay? So of course, this one, the non-alternative argument, is the one that is actually built inside the atmospheric retrieval model, because we know that the atmospheric retrieval model has, right, different different iterations, okay? But then we also know that the atmospheric retrieval models suffer from the problem of incompatible models. So we have to be very careful. We have always to consider the whole family of different best matches that come from different models, okay? And then we can say that this family of models provides objective model knowledge, as we said before, okay? And that there are no alternatives with respect to that family, okay? Moreover, it should also be mentioned that even though the non-alternative argument is weak, okay, and it suffers from the problem compatible models, you know, there are also the other two that, you know, it's kind of complementary and is strengthened by the other two arguments. So for instance, let's think that our model gives as output A, okay, and A, but not its outputs of our models is consistently supported also by other meta-empirical arguments, so like the meta-induction arguments, okay? Then, of course, we should have confidence in A over its alternatives, and we can say that A is viable, okay? So, one might object to the use of meta-empirical tools, confirmation tools, to appreciate the saliency, the epistemic saliency of the atmospheric retrieval model by saying, well, but they're not really about the inner mechanism of the models, right? These tools are something that over and above we can apply to the atmospheric retrieval models, in particular to judge the viability of the outputs of this retrieval model. But per se, these modeling techniques do not have, you know, epistemic importance that can be related to the empirical confirmation framework. Well, for the non-alternative argument, that's not true, because we saw that it's built inside the retrieval models. But we could also, for instance, with the choice of priors, we could also use the information, the knowledge provided by meta-empirical arguments to basically make the retrieval models epistemically salient. Okay, we can choose the priors in such a way to prefer some hypotheses instead of others in light of these meta-empirical arguments. Okay. So then, are we justified in placing trust in those models? Well, of course, here we are just, even with meta-empirical confirmation, of course, we are just talking about viability, which is much weaker than truth. Okay, we can't say that the outputs are true. Okay, it's viability and it's about a specific research context or epistemic situation. However, viability is an epistemic virtue that is not merely pragmatic, and so it is epistemically salient. Okay. It means that if we say that hypothesis is viable, okay, then we say that we can trust that it will represent empirical data that will be collected in the future, okay? And so it establishes an epistemic goal in its own right, okay? So here it comes to my conclusion, very last minute. So first of all, we can say that exoplanetary science is a young discipline that still has to build its identity and respect, okay? And what I saw while working in Bern is that there is a growing attention among astrophysicists to philosophical problems that are really that are really related to the scientific method of exoplanetary science. So it's really the time for us to engage in this science, and it's also the time not to downplay or overlook its methodological challenges because that might affect its credibility in the long run. Okay, so with this paper and with this talk, I would like really to go in this direction. Okay, then regarding more conclusions, well, I do think that atmospheric retrieval models are more epistemically robust than just theory-based or just data-based models, and also more than independent models. Okay, they inherit their epistemic justification from both the theory and data. And I do think that they have a representational function that has a modal dimension, okay? Well, they may or they may not provide epistemic justification, okay? Depending on if, they pass the test of meta-empirical confirmation, if they are using meta-empirical confirmation tools, if these meta-empirical confirmation tools are built inside their models, okay, these models. If so, I do think that they provide epistemic evidence and the atmospheric condition that they give as output are viable. And I would like to thank you, as I would like to thank many other people. Thanks.
All right. Thank you very much for this lecture. So we have time for questions. Before we go to the questions, let me remind you how we're going to be proceeding. Please write your name in, go down to the bottom of your screen, click on Q&A, write your name there. No need to write the question, and I will promote you to a speaker so that you can ask your question to our speaker directly. Carl, I guess you have a question? No? All right. So Siddharth will be the first one. Siddharth, I'm going to be promoting you to speaker in a second. All right. All right, Siddharth, floor is yours. You need to unmute yourself.
Hi. Okay, so I guess, yeah, so my question was about to what extent, I mean, so these models seem to be very, they fit very well with the Bayesian framework, right? So you generate a bunch of hypotheses, you calculate a bunch of likelihoods, and then you sort of try and figure out what the posteriors are and so on. And then in some sense, can't we just say that's the epistemic value? You get a credence out in the hypothesis, and that's it. That's the best you can say, right? Like, I mean, do we really need to? So I'm just trying to understand what the further problem is.
Yes, thank you. Yeah, hi, Siddharth.
Nice to see you.
And thank you for your question. Yeah, so definitely. So they use traditional Bayesian statistics, and you could just say that this is the kind of confirmation that you get within Bayesianism, and that's it. Okay. So it it seems to me, however, that if we use the meta-empirical framework here, okay, and we can incorporate it within the models, the atmospheric retrieval models, we would, so of course also the meta-empirical framework, the meta-empirical confirmation framework uses Bayesian statistics, okay, but the difference is that in order to have a confirmation for them, you need a substantial increase in the probability. So this is why Richard David uses 3 different meta-empirical arguments to confirm Y that then will confirm H. Because the incremental in the probabilities must be substantial. Otherwise, you will not reach a confirmation. So in this sense, I think that, yes, one could say, very, okay, this models just gives you the kind of confirmation that is in line with Bayesianism. But I think that a further step would be, well, they could be, their outputs could be a little bit more reliable if we also incorporate the meta-empirical confirmation framework, because in that framework, to have a confirmation, you need a substantial increase in probabilities. Does it make sense, my answer?
Right. But so why do we need that sort of judgment of confirmation other than just whatever credence boost we get? Is it because we need to make decisions about when to publish and stuff like that? So like what? So just attaching the word confirmation, why is that so important?
Oh, I see. So so maybe I come from a very kind of like pragmatic point of view. So basically we run these retrieval models and then we get the output, okay? And we can say, okay, well, this is confirmed in a Bayesian sense, okay? But if we know that actually there was this meta-empirical reasoning incorporated in the model, and so there was this substantial increase in probability, then I mean, if we build already models with this kind of meta-empirical tools, then I think they would be more significant epistemically. But I understand what you're saying, that maybe it's just a problem of like the word confirmation.
Okay, thank you. Yeah, we can continue
Yeah.
later. Thank you. Nice.
Thank you. Thanks.
Thank you, Siddharth. Carl, please join us and turn the camera on. Very good. All right.
Visible somehow?
Yeah, Carl, it's probably better if you come to the camera.
Right. Well, hi, Vera.
Hi.
I just wanted to ask, well, I had several questions, but one is a verificatory question. When you talked about the meta-inductive argument as part of these meta-empirical framework that you were giving us at the end, you talked about the having some data about the reliability of the ARMS, the atmospheric retrieval models. And it sounded like you were talking about a track record that was already empirically established, which would require having applied these tools and then go and somehow have direct evidence. And so what I was wondering is part of this meta-inductive argument that they've tried out these atmospheric retrieval models on like Saturn and Jupiter inside our own solar system. And we've also sent probes there. So we have sort of much more direct way of confirming the output of the atmospheric retrieval model, or am I totally not understanding?
Yeah, no, I think that you spotted a very weak aspect of the meta-inductive argument. Because no, actually, the argument does not rely on the fact that we had a track of direct observation. So it just says that in the past, okay, we, retrieval models gave us as output a similar retrieved quantities that are given now for a spectrum that was similar to the spectrum we got now. And so most probably the two planets were, kind of similar. But you might argue and say, well, that's very weak, right? Because, if if the outputs that we got before are not that reliable, then how we can run this meta-inductive argument? Okay, because this meta-inductive argument relies on outputs that were given by retrieval models, but they were not very cogent, right? Because they were based on indirect pieces of evidence.
Well, okay, thanks for clarifying that.
Yeah, I mean, yes, definitely. I mean, I was also, one of the problem that was pointed out is that this MIA is indeed weak.
Okay.
Yeah, thank you, Carl.
Thank you, Carl. Maddie had a question next, also at the center. So Maddie, why don't you join us here? Okay, thank you, Maddie.
Can you see me? Okay, hello, and thank you for this talk.
Hi.
I just want to ask you about the inconsistencies between these different models. Could you elaborate on the kind of inconsistencies that exist among these models? What kind of inconsistency?
Yeah.
And can we find a common core between different models, different atmospheric retrieval models? And if there is a common core that they share, can we adopt a more realistic view about this common core? Well, thank you.
Yeah. Thank you very much, Maddie. So, yes. So the level of inconsistency is basically spread at three different. The inconsistency is spread at three different levels. So first of all, it's already present at the level of very idealized forward models. Okay, so even if we just hypothetically imagine that we have just one kind of absorber, one kind of gas that plays the role of absorber, then we already get, we might get different results because if, the modeling assumptions are different. Okay. So then, of course, things get much more complicated when the forward models are more realistic, okay? So if we have a composition of the atmosphere that is much more complex and not with just one observer, that is really impossible, but we have many, then, of course, the models are very different, okay? And things are even worse to the retrieval models. So what are these inconsistencies about? Well, first of all, there could be models that lack some chemical components or they have different ones, but this is a bit rare. What most of the time happens is that where maybe one model has very different abundances of the very same component, or that we have the presence of hazes in one models or clouds in one models and not in another, and so then the abundances are different. Okay, so these differences play out at different levels of several or few tens of ppm. What does it mean? So even if, so no matter whether our error, is small or, it's big, then we would have differences, okay? Even differences of several sigma. So this means that, of course, characterizations of, abundances of chemical components, of even like temperature, pressure, then are very different. Okay, so is it possible, your question then is it possible to have a common core? Well, sometimes yes, sometimes there is a greater convergence, and maybe because the spectra are less uncertain. Okay, maybe because the spectra itself is very clear. Okay, it's of very clear interpretation. Okay, as I see in the literature, always to try to make these models compatible, and so convergence are a little bit artificial. So sometimes, they use some recognition pattern algorithms to model the initial parameter space. So this will analyze the spectrum and establish what is the initial parameter space. Okay, sometimes they have to really manually adjust all the assumptions. Okay, all the auxiliary assumptions, the modeling assumptions. Okay, and so I don't see a real kind of clear way in which we can see like a stable pattern in which all different compatible models in any case they share some core, something that is in common. Okay, is it okay?
I think it is.
Okay.
Lucy, why don't you join us? All right, she's also at the center.
Yeah, good.
All right, thank you, Lucy.
Okay. Hi Vera, thanks for this. This was really interesting.
Hi, Lucy.
Hi. So one of the general conclusions you draw is that the representational function of the ARMs is to kind of map out modal structure, right? So you're mapping out possibilities, and then you kind of eliminate the possibilities that are not viable, right? So I was just wondering how generic you think this conclusion is, because you've talked about it in the context of ARMs in exoplanet research. So I'm just wondering if you think this type of method and this kind of conclusion, so what we get out of these methods at the end, so the modal structure, whether this way of thinking applies to, say, other areas of astrophysics or outside of astrophysics altogether, so other areas of physics.
Yeah, thank you for this question. Yes, so definitely retrieval models are used in many different areas, at least of physics, as far as I'm concerned, so definitely particle physics. And I do think that in all cases, since the structure is the very same I have described here, they fulfill this job of mapping the space of objective possibilities and then ruling out all the different possibilities until they have the best match. Of course, depending on the quality of your data, depending also on whether you have, you use priors in a kind of significant ways. For instance, the teams I was working with, they were just using flat priors. But, maybe, I don't know, in other different cultures, like scientific cultures, there could be like a use of priors more or less well motivated and justified. Then maybe you could have a maybe stronger how can I say, you have a stronger reliability, like these models might be more strongly reliable. Okay, what I can say with this kinds of model, with the kind of data we have, with the kind of theoretical knowledge we have, I think that the best thing we can say is that they model the space of possibilities. And I do think that this is for all retrieval models. Yes, thank you.
Good. That was the last question from the center for now anyway. If someone has a question at the center, please again write your name and
Yes.
we'll bring you here. If someone has a question among the attendees, please write your name in the Q&A box and I'll bring you in. If not, I will ask a question myself. It's mostly clarification question, really, and I had two small ones. The first one was I was not quite sure why you thought that combining a data model and combining a model derived from a theory was actually necessarily making the model more reliable. You might think rather that you're inheriting the uncertainties from both sides. And in fact, if one side is more reliable than another, you might think that combining that side with another side might actually make it less reliable. So it's far from clear why just by combining, you thereby get an increase in reliability. I thought I was going very, very quickly there. It really depends on the epistemic status, one might say, of both sides that somehow are combined in a retrieval model. So that was the first question. And the second question, I'm not sure what you mean by objective model knowledge. I just don't understand what that is. Objective in what sense? Knowledge in what sense? No, I think what we learn is we learn what is possible according to the models we have. So the right model in that case is might, is not can. And might is, under any possible understanding, it's an epistemic model. So it just tells us what is possible in light of our assumptions, maybe in light of our belief or in light of our evidence, not quite clear. But objective model knowledge? I'm not sure. I don't know. I'm not quite sure what that is, and I'm not quite sure how we could get that this way.
Yes, thank you, Edward. Yeah, okay. So concerning the first question, yes, I know that might be a very weak point of the talk. So my idea is that basically we want to get a cogent representation of the system. And I think that the more we constrain, so, when you have these very complex modeling techniques, okay, then you have to make so many different assumptions and choices that sometimes are a little bit arbitrary. And I think that the more the model is constrained, the better it is. And if it is constrained by both the theories and data, then it's a kind of it's the best possible words we can get. Okay, so we have both the data and the theory. Yes, it's definitely sure. I mean, I definitely agree with what you were saying. I mean, if for instance, like in this case, we have a kind of theory that is well established. It starts from first order principle, conservation principle, and our data is so uncertain. Then maybe it's better not to consider the spectrum. Okay, but this, of course, it would be kind of impossible because we cannot guess, right, what the atmosphere could be on like WASP 76b. So I don't know. I think that if I evaluate the mechanism itself, it's much better that it's constrained by both. Then, of course, we need a contextual evaluation of whether the data is too noisy or the theory is too problematic. So definitely, I allow that there can be a contextual evaluation. But yeah, it seems to me that the mechanism is better if it's constrained by both. Then concerning, yes, the second question. Yeah, so definitely talking about objective model knowledge is problematic. Thank you for pointing it out. So I put objective just to stress that it's not my subjective credences or just the kind of creativity of a scientist that comes that wakes up in the morning and think what might be possible, but it's a kind of knowledge that is constrained by the theory and the data. And so when we carve out the space of possibilities, then you know, it's a kind of objective the way we carve it out. Maybe, yeah, I got like different literature mixed up, because in Bohmian mechanics we talk about objective epistemic uncertainty, and so maybe, yeah, that was a problem. But yes, also concerning knowledge, what does it mean? Yes, I mean, we got to know what might be possible and what is most probable. So in that way, it's kind of like model knowledge. But yeah, I think I should probably work out better and flesh out better. Yeah.
Good.
What
Good. I mean,
Thanks.
I think the last thing you said was, I mean, the penultimate thing you say was right. I mean, there's a contrast between arbitrary and non-arbitrary, right? So it's
Yeah,
not
arbitrary,
it's not just what you're thinking, what as you rightly put it, is what the scientist is thinking might be
Yeah.
possible. It's grounded in some set of other resources, either theoretical or empirical, the data. So it's not arbitrary. In that sense, it's objective, when objective means non-arbitrary, but it's not objective in contrast to epistemic.
Yeah.
Right?
No. Yeah.
Good,
Yeah,
good,
exactly.
good. Thank
you.
That's really helpful. Any other question from the attendees or people at the center? I'm going to count, as we do for an auction, up to 3 in case someone raises a hand. 1, 2. Lucy has a question. So, you know, it works just like at an auction. Lucy, please join us. Turn the camera on and turn the mic off. Right.
Yeah, it's like a quick
Hi,
follow-up,
Lucy.
I guess. Hi, quick follow-up to some of the things that have already been asked. So with this modal structure that your models are mapping out, have you ever come across cases where you have like non-intersecting sets of possibilities that are allowed by different models of the same target phenomenon? So you have a level of underdetermination with respect to the modal structure. Is that something that ever happens? Or do we kind of assume that the modal structure that you get is kind of doesn't have this interpretational problem?
So I'm not sure if I am understanding the question correctly. So I can see that there are cases in which even the parameter space is different and is carved out differently. So you carve out the parameter space differently. So you have different distributions of probabilities.
Yeah.
And
I
then
guess, yeah, I guess
am I understanding the question?
Yeah. So I guess what I'm wondering is whether you have models with the same parameter space, but which sets of hypotheses are possible according to those models are different. So whether you have
no.
Because we wouldn't want that to ever happen, but I'm just wondering if that's
no. Thank you. Yes. Yeah, no, I never encountered this. Yeah.
All right.
Thank you, Lucy.
We're reaching the end of this Q&A. Thank you very much, Vera, for joining us for, I believe, maybe the last feature for Fellows presentation this academic year. And we hope to see you in person here on this side of the Atlantic, or maybe on the other side of the Atlantic sooner than later. All right, and thank you all for joining us today.
Thanks all.
Bye.
Thanks.
Take care, Vera.
Bye. Bye.